цифру 4%. Нет, это две системы, которые говорят, что эта цифра у него в голове там открытая.
So it's
Да, мы очень уважаем Трампа, он нам очень помогает.
so I think it's time to begin. Our today's speaker is Jakub Kryczka from BIMSA. You see the title. Well, I'm glad to open the spring session of 2025. Jakub, you're welcome. Please begin.
Трамп ведет себя и он врет, не важно, какой церемонии, а вот Трамп не. Она это все писала мне, напротив вешена. Она сестра Бога.
Jakub, you should switch on your microphone.
Okay, how
okay,
can
now
you hear me all right now?
Okay, and make it full screen again.
Perfect. Sorry about
Yes.
that.
Yes, perfect. Please, you're welcome.
Okay, yeah, so thank you very much for the opportunity the invitation to speak. So I have 1 hour, is that correct?
You a little bit more, 1 hour and 15 minutes maybe.
Okay, all right, just so I know what the pace is here. So it's I'm very happy to get the chance to interact with this community of researchers and talk about something I find very interesting, which is this geometric setting for PDE in various maybe non-conventional contexts. And in particular, what I want to discuss today is how maybe this PDE geometry that we all know and love, formulated in the jet bundle approach and based on these homological techniques, can be adapted with a mix of some other techniques to treat some very singular situations and can be globalized. And I think over the course of this talk, I'll try to truly convey what I mean by global. I think is one of the most important adjectives here to emphasize, and singular in certain instances, as we'll see. So it's really based on this jet bundle approach and studying the formal integrability of these PDEs. So throughout, we're going to be assuming we're in the context of studying infinite prolongations of systems of nonlinear PDEs. And the idea is really based on to mix the application of these functors of differential calculus, which have been applied so well to the geometric theory of nonlinear PDEs at this jet bundle level by noticing the structure sheaf of these PDEs is a filtered, geometric filtered algebra, and so can be suitably adapted. And this has served as a very convenient formalism for, sort of going around these infinite dimensionalities or profinite dimensionalities of these spaces. And so in general, it's a sort of understood fact that if you have some maybe singular space, this singular phenomena can, in order to treat it properly, you should sort of enhance, or in the terminology I'll be using today, which is more common, is derive a lot of your so-called functors, or sort of enlarge your class of objects that they can sort of detect these refined invariants you need. So a typical example is a tangent space. So in the context of PDEs, we'll be looking at the tangent sheaf of a PDE. In general, it will need to be enhanced to some complex. And this complex will contain homotopical information. And so a prototype example of when you might want to, change your perspective or enhance something, but retain the original information, is when you are looking at so-called a causal Tate resolution of a jet bundle, or this on-shell algebra of functions. So for now, this D algebra we can just understand it as an algebra with the action of differential operators. And so this will be through the Cartan distribution. So basically, when you have some generically irregular ideal in this setting, you want to, usual commutative algebra tells us to replace this. So make a causal Tate resolution, or in a suitable setting, this can be a canonical operation, actually, in a suitable category of algebras, as we'll see. And the idea is then, of course, because it's a resolution, you H0 of this just reproduces your original on-shell algebra of functions. So this is a very nuanced statement, really, goes back to, I guess, Kontsevich, which is his sort of so-called hidden smoothness philosophy, which is that if you have some mathematical object, so for us, it's going to be some solution space of these nonlinear PDEs, suitably enhanced to and take into account some symmetries and some possibly non-transversal intersection loci of our PDEs, as I'll mention throughout the talk. And this hidden smoothness philosophy is really saying, okay, so you have a moduli space parametrizing some objects, and generally it's very likely it's going to be singular. There might be some components of it that have different dimensions. So as your objects move around, they jump in dimensions. So this isn't so good, but this is kind of indicating to us that there's a sort of DG or derived version. So with these boldface R, I'll write in front of everything to really say it's the same object, but viewed in a more suitably enhanced setting. And in fact, this derived object will be smooth in a derived sense. So in a DG differential graded sense, or a simplicial sense. And the idea is that there is a sort of truncation, in fact, it's called classical truncation, back down to your original moduli space. In the same way that we viewed this causal Tate resolution so H0 is exactly such an operation. So you enhance by forming a resolution, and you can go back to reproduce your original object. As you see, this is a generally irregular ideal, so will most likely this is sort of our indicative singular object in this case. But the idea is you want to study this derived moduli space, or this causal Tate resolution, not just as taking it from some other object, but as an object in its own right. So in this sense, it's really about enhancing your object. So in general algebraic geometry of schemes, stacks, and you can look at them for their functor of points, and then you pass this so-called derived schemes, derived stacks, and all of the associated objects you like should have some kind of derived notion with them usually. And so for the causal Tate example we saw before, we want to ask, okay, so we built up this resolution by adding in some variables that kill the cohomological degrees of freedom and ensure that everything is like a regular sequence defined by our relations in this ideal on the jet bundle. But we don't necessarily just want to keep the H0 part. We want to look at it as a graded algebra in its own right. And so we want to look at the spectrum, or find some category where the spectrum, or you can form a scheme or space with that algebra as its functions. And indeed, if you then use this classical truncation operation, it really does produce spec of the classical, so H0 of that, which will be just your original object. So it's sort of a homotopical thickening. And it's very mild in the sense that in this suitable homotopy category, or suitable homotopy environment, it really is a homotopy equivalent object by design, which is really the statement that it has the same homotopical information, but it's bundled together in this other object. So this is just one very nice example that we would see in jet bundle geometry, and in the BV formalism, this including symmetries into this account also gives such objects, but we'll see that in due time. So in reality, these are viewed as some kind of generalized functors. So they take values in your space of algebras or schemes and go into some higher category of objects. So here I write space down here for to mean basically simplicial sets or infinity groupoids. So it means you have like relations, and you have relations between relations, and so forth. And this is also inherent in all of the categories we basically work with, which is their infinity category. So it should be souped up in a suitable sense that you have homotopy coherent relations between your objects. In practice, how you do this, for instance, if you have a derived category of, so let's say, co-chain complexes, you would formally invert your weak, if you just have a category of co-chain complexes, a derived category is an object of this type where you're formally inverting weak equivalences. So quasi-isomorphisms, you view objects up to quasi-isomorphism, it's very similar to this. And this is what we want to do with objects maybe not of a linear nature, for instance, objects of a derived category, but of a maybe more nonlinear nature, which is exactly the kind of objects that our PDEs with singularities will give us. So again, I say here, unfortunately, it employs some heavy infinity categorical technology. So I'll try to sweep this under the rug as much as possible today, and just to emphasize what is the real big main differences from the classical PDE geometry we know, and maybe try to pinpoint some of, it's not just about enhancing the objects and finding new ones, it's about maybe using these homotopical techniques to learn things about the objects we already know and work with. So the upshot is that we can study global objects over not necessarily smooth spaces. So over your X will be a space of dependent variables for us throughout the talk. It doesn't necessarily have to be a smooth manifold or a variety or complex analytic space. It could be some kind of orbifold even. Why would you want to do that? Well, for example, if you want to study global spaces of solutions to, let's say, the equations, Einstein field equations in GR, you're looking at some kind of Lorentzian, so globally hyperbolic space-time. So it's a causal manifold, and you're taking equivalence by some diffeomorphism group. So it's really a stack of objects up to this symmetries. And this is just one notion that we can play with here, but also we can work with parametrizing families of PDEs. So this really touches on the moduli interpretation we're working with. So here, this R sol for us is again just going to be solutions, and I'll try to connect what this looks like as we know it. It's these sections of our bundle that are infinite jet prolongations, and they factor through an equation manifold. So we'll see this in due course. But everything is up to homotopy, which is quite an interesting feature, as I'll show. So the idea is that so we can work with nonlinear operators that are fiber-wise. So over this, if our space X is parametrized by a space S, so it could be a smooth stack, or it could just be some parametrizing space. But in practice, we can take it just to be a point, really, throughout this talk. But it's important to emphasize we can really work in families. And then we study fiber-wise nonlinear operators, maybe with some additional conditions, ellipticity, or whatever you would like to impose here. And these, of course, are viewed as through the duality of kth order differential operators and functions out of kth order bundles of k jets. We can view this as inducing sort of a map on sections. And again, this is boldface R sect to be like some stacky or higher version of sections. And I'll tell you, really try to show you what is the big deal about doing this. So basically, the solution space as we know it is some kind of kernel. It's basically saying we look at the functions that are annihilated by the operator. Okay, this is straightforward. The idea is that in general, these kernels should be taken in a derived or homotopical sense. So it's some kind of homotopy fiber product. And if you formulate it appropriately by this diagram, in fact, it doesn't hold up to the like on the nose. So you're not having some function annihilated by p equals 0. That's not the data. We have additional parametrizing homotopies. So you have paths that record all of the solutions that are homotopic to 0. And this is an important feature that allows us to actually work with maybe and detect solutions that might not otherwise exist, but they might exist, up to some additional data. And this additional data can be chosen based on your geometric setup. So here, this sections, these are these stacky objects. So usually I'll underline it to make it to emphasize these are viewed from a functor of points approach or as a functor. So it means you can take some parametrizing space that we should have specified if we were in our context. So we can think of it as just a manifold. And so then we look at T parameterized sections. And this turns out just to really be as you would expect it. So T parameterized sections from X to E. And these are they're sections of your bundle. Okay. And so why should we be working with such general objects to begin with? So why this boldface R without really giving you details about it? It's because if we're thinking right from the get-go, with everything classical, then we really don't have all equalizers in our category of let's say, PDEs modeled on vector bundles over a smooth manifold X. In that, if we take two operators mapping out of the K-jet space from some vector bundle E to F, in general, we won't have that this fiber product that we form here, this E0, this equation manifold, in general, without maybe a priori some transversality conditions, will not exist as a smooth manifold in its own right in the category. So we leave the category, but we'd like to, enlarge our category by sort of formally adjoining all such finite limits, so that we really do have all of these. And you can do that in a couple of ways. But one way is that if you pass to a sheaf topos and view all these objects sort of as the representing objects of a sort of by their functor of points, then in sheaf topoi you have such equalizers. And so it's not such a big scary task to try to address this question. But what does become the problem is that maybe if these solution manifolds have singularities, they're not smooth in their own right, then this functor, even if you will not be representable in this sheaf topos either. So you should then look at PDEs modeled as certain sheaves so that you have these limits, but you allow your objects to vary in a larger category of maybe DG or derived objects, where you're maybe allowed to have non-transversal intersections, and maybe you're allowed to view objects like your manifolds viewed up to group action, and without any assumptions on the group action. For instance, you don't need properness or anything like this. And that's the idea of derived geometry, is we enhance from a functor of points approach, you enhance the objects that you take in on your functor to some DG version, and you enhance the target of these functors to some simplicity enhanced, or like spaces, infinity groupoids. And that's sort of the difference between, on the one side, enhancing the derived or intersection, so fiber product problems, and then on the target is enhancing to account for symmetries. So this will be the main uses of the terms derived and stacky here. It's just symmetries and lack of fiber products. This is essentially what will boil down to. And it's not super important to know what a stack is. It's just a functor valued in some higher object, and maybe on some homotopical site or category. So in this case, from this description here, if we take some T parametrized solution now by this description, it's a map in some category of stacks or some higher functors, and it amounts to, again, some T parametrized section, maybe over S. And it satisfies your equation. So this is the zero section in your bundle F over X, but this again is not an equation on the nose. It's implicitly built into the machinery. This is not a condition we're asking for. It's extra data that's given to us by enhancing to homotopy fiber product. So it's a path between your solution, and so it's a path specifying that your parametrized section is a solution. Okay, and so what does this really mean for formal reasons? Well, so these are Soll spaces or some higher object. So for formal reasons, if they are representable, you can form some kind of tangent functor. If you just think as maybe some space, like if there are spaces of homomorphisms, you can look at the tangent space of this, or space of sections. And if you ask for if it's, again, representable, it'll be representable not by some tangent space, but this object here. I write T of P, boldface, again, to emphasize that this is actually a complex. And in the PDE setting, this actually really does amount to linearizing our system. And linearizing in the sense that we're familiar with, if there's no DG structure happening, that this representative object is really the operator of universal linearization. And so it turns out that in general, you write this as some kind of complex of D modules, and as a complex, it has cohomologies. And these are really the deformation theory of your solution space, assuming that these objects exist. And so you can have parametrizing spaces of your deformations of a solution, obstruction spaces. So these are really interpreted to recording the non-smoothness of your moduli space, and then also recording your infinitesimal automorphisms of your solutions. So there's some usually accepted interpretations of these spaces that I write here, H-1 and H1. And in fact, it reflects the global behavior of, let's say, a space of solutions modulo some gauge action or some group action. And again, as I mentioned, this is really some jumping of the dimensions of these tangent spaces that are built up in your complex at various points. So this means that the stabilizer of a solution by this group action changes. And what can we see in like a very concrete setting is if you have some family of solutions in a PDE viewed as these integral submanifolds, and maybe it's T-parametrized, so one parameter family, you could cook up, if you're extremely pathological, you wanted to cook up some group action that specifically moves the one parameter family of solutions in such a way that it intersects them with themselves. And this would be an example of a self-intersection or multi-valued solution in the standard sense that is viewed as a stacky phenomenon. So typically what people would do, especially if you want to work in, let's say, moduli spaces of Euler-Lagrange equations, and instead of working globally, it's very difficult. These objects are very hard to get your hand on. So you pick a solution, you work locally around the formal neighborhood of the solution in the moduli space. So this is a tangent space of that object. So this is a big DG space. It's quite huge. So DG in that its function algebra is going to have some differential graded structure. And the formal neighborhood of a point is some kind of Chevalier-Eilenberg algebra built on some L-infinity algebra. And this is really the tangent complex of that point. If this is not a DG thing, then this is really the just the tangent space of the object. And this is typically what people do when they do perturbative field, the perturbative field theory. And this L-infinity algebra is sort of has the brackets that you would see in this BV formalism. But we want to work ambitiously with the global setting. And so this is just a reflection of this phenomena here. So as I mentioned, this D floating around here is going to be referred to the sheaf of differential operators on a space. So it's important to understand that when assuming that this D modules or D algebra stuff is floating around, that our space X should be basically, it doesn't necessarily have a globally defined sheaf of differential operators. For instance, if it's a singular space, it might not have such an object that's globally defined. And so there's a convenient alternative approach to work with, which is a different way to encode flat connections in bundles or in maybe nonlinear objects, as we'll see. But in any case, the main point of the theory of D modules, we really want to be trying to see what we can enhance them to in the nonlinear setting and apply it to this jet bundle geometry are the de Rham complex functor. So it's on some bounded derived category of objects. Again, this is for linear stuff, so we don't have bounded derived categories for algebras. So this is, we need to look somewhere else. But this R sol functor is really derived functor of the internal hom. So this is where this maybe terminology derived also borrows from, is that it's really classic homological algebra is the derived functor. So usually you view, if you have some operator P, you can study a D module as some kind of defined by some co-kernel sequence. And then it's really viewed as the representing object for this hom functor, this D linear hom functor, because, you know, mapping, if you evaluate it on, let's say, the structure sheaf, it really does, it annihilates on the operators coming from, or the operator P, or if you have an ideal spanned by multiple operators, it annihilates on those, and this is really just a kernel. So the cohomologies of this are the X groups, homologically speaking, And they have nice interpretations. For very simple cases here, you as the kernel and the co-kernel of your operator. And so the higher x, so x1, which would be h2, and so forth, are higher order compatibility conditions. So this is important to note here that a D module and its X groups and these R sols is really recording some kind of homological information about your operator. And so when we go to some kind of nonlinear setting and we linearize, if our nonlinear object is maybe derived, our linearization, our tangent object will be a DG object. So it could be a complex of D modules and will live in an appropriate category like this. And such a formalism will apply. But this involves first telling you what the DG version of linearization would be, and fixing some global subtleties with this. For instance, a choice of a solution. Another point to maybe mention, which I should have said here, is linearizing around a solution produces some L-infinity algebra or DG Lie algebra object. So it shouldn't depend on a solution, your linearization. And in fact, the cohomologies, what changes here is the cochain complex, so the underlying vector space of this cochain complex actually remains the same. But what changes is the differential. So it depends on this choice. So it means your L-infinity algebra structure basically can change, but from what I've seen in a lot of the physics literature is that actually for various different choices of your solution, maybe it's a background vacuum solution, or for some, let's say, phi-4 theory or scalar Klein-Gordon theory, or it's some just generic solution, is that the DGLAs, differential graded Lie algebras, are you can find a retraction of one onto the other, and so they are essentially homotopy equivalent L-infinity algebra. So there's L-infinity quasi-isomorphisms. So it doesn't really pose a big problem. So let's see how the timer's going. Okay, so the main message for today, because I have a lot I would like to say, and it's always the case when I talk about these things that I run into time constraints. So the message is absolutely just I want to convey to you that we can, enhance our setting for nonlinear PDE geometry based on jet bundles in a way to account for some symmetries, some singularities, and in doing so, we can learn new things about the classical objects. So one of them, as we'll see, which maybe you have guessed by now based on the title and from what I've suggested, that, okay, if we have a tangent space to our PDE and it becomes DG, it means there's an additional homological grading. And so if we form the variational bicomplex of such a structure sheaf of a DG nonlinear PDE, it'll have an additional homological degree. And so this is essentially the title, or I say bicomplex is in the title, but it's a derived bicomplex or a tricomplex. And I want to comment on some of the secondary philosophy that happens in this setting. So maybe just a really basic example to even exemplify what I'm saying is if we just look at some punctured disk in the complex plane, and you have some coordinate variable z, let's say, you can look at some couple different nonlinear equations. So the first one is just these are just differential equations. They're not necessarily partial differential despite my poor notational choices. And you can look at a family of solutions. And in general, it's a general principle that if you just have, an operator acting between two spaces, that the tangent complex is really just the differential of this, and you place the two terms in degrees 0 and 1. So taking that on good faith, it means that for us, the tangent operator that defines this tangent complex is really just the operator of linearization. And you can compute, so this is sitting in degree 0 and degree 1. And if you look at a generic family of solutions and you linearize around it, you can see that there's some conditions actually that would arise naturally for the original PDE as it's being framed that would lead to non-trivial higher cohomology. So it's not necessarily the the tangent space of our linearization operator. So in the nonlinear world, this is what we would expect as the kernel of this. These are the symmetries, right? So we have some kind of higher dimensional space that we need to account for. And this happens in some well-known pathological types of PDEs, like the Clairaut equation. And in fact, has become apparent that maybe these higher order tangent spaces, higher order cohomologies in the tangent complex that don't vanish, have interpretations in the classical geometry of the object. For example, in the singular integrals related to these families of solutions. But this is just meant to exemplify that even in some very, very special or very ODE settings, that you have some kind of object with non-vanishing cohomology that might connect with, regular classical features in these geometric PDEs that needs to be interpreted and needs to be understood what it means for these, what it means to have non-vanishing higher cohomologies in these cases. So to get to where we'd like to go, we should discuss probably what most of you are very familiar with in this. So set some context for PDE. So we know it's some system of equations and some vector functions and some dependent variables with the usual multi-index notation. And as usual, we have some submanifold or some subspace in some space of k jets and m dependent variables and n independent variables. So again, this is finite dimensional as usual. It comes with its Cartan distribution, and we want to study, so modulo the typical assumptions of formal integrability, so that we have all the differential, it's differentially consistent. We have this infinite prolongation, and we want this not to be an empty or equal to all of the jet space, so just the empty PDE. So the idea is really that, as we know, we have these total derivatives, and the solutions are these integral submanifolds of this Cartan distribution. And so one of the key points which I want to emphasize is that this really can be viewed as an action of the sheaf of differential operators on the base. So of course, it's a flat connection. And so a D module generically is, well, it's a special, a D module is a more general version, I guess, of a case of you have a vector bundle with a flat connection. And so in this case, we can view it as a compatible lifting of the action of functions on the base and by this vector fields here. So this is what I'll say is sort of the category of PDE. So PDE Vinogradov, I'll write it up there. So to emphasize, this is to be non-singular PDEs. So these are modeled on vector bundle objects over some smooth manifold X. So the free variables are in X. And so, of course, there's lots of examples. There's the tangent bundle to your bundle. You can also look at it as just points, the manifold itself with points. So foliations also give an example of this. Poisson manifolds as well, and then obviously the jet spaces and infinite prolongations. So again, then it's probably well known in this community that the jet algebra, the jet functor is a coalgebra, as a comonad, and so you can study some associated category of coalgebra objects. And what's very convenient in this setting, which I note here, is that obviously morphisms in both of these categories preserve the important structure in our PDE, which is this Cartan distribution. The way they're defined in the Vinogradov category as these distribution preserving maps, it becomes very difficult once we try to do some kind of homotopy theory of these objects. And how do you glue together pasting these objects in a homotopy coherent way? It's not clear to me, at least, how this gluing notion of these morphisms would work. So this is what is motivating this section. I'm talking about context for PDE geometry of differential equations, because this coalgebra one and studying coalgebra maps, J infinity coalgebra maps, is a nice way to go, because the comonadicity of this object extends to much more general settings, as we'll see. But the key point of all of this is that the underlying object that is wanting to be preserved is really this the solutions, which are these integral submanifolds. And so everything should be cooked up that it respects this distribution, this Cartan distribution. And so in the setting of, if you view it as the structure sheaf of, let's say, the infinite jet bundle or any of the objects that we just talked about as an algebra with the action of the sheaf of differential operators, it's a commutative D algebra. And it means we are in a category of commutative monoids in the category of D modules. So that's quite nice. And it's actually a universal construction in this one. So it's adjoint to forgetting the connection. And what's nice about this is we don't really need to ask for any sort of recipe to preserve this distribution. The internal Hom in this category are D-linear. It's everything's, you can cook it up so that it's a D-linear. These are Hom functors we saw before. And so this is really the condition that we want to have preserving this distribution. So this is really nice because it means we can formulate using commutative or differential calculus just directly applying it to the category of commutative D algebras. So every functor that we would know is, so you have derivations, and it's representative objects, so Kähler differentials, and multi-vector fields and so on. Everything is now just taken to also be D-linear, which means commute with the action of this lifting of the vector fields, which are the total derivatives. Okay, so this is category has just one little nuance, which comes from D-module theory, is really that it's because the sheaf D of X is not commutative, but it's close because you can twist by this dualizing sheaf or the canonical sheaf of your variety, and this gives a autoequivalence of left and right D modules. And this is important for what comes when we have to sort of dualize our objects, because if you dualize a left D module in the, let's say with respect to the first slot in a Hom functor, it produces out for you a right D module. And so you should twist again, applying this this leftification, or for lack of better terminology, operator, to get back and have a functor from an endofunctor on your categories. Okay, so for us, just affine D schemes are going to be just commutative, the opposite category formally of commutative D algebras. And we read it as spec D of an algebra A. And this actually works. You can prove that spec of the universal jet D algebra is really the jet D scheme, as you would know it. But this is very useful because it can glue to larger objects, not necessarily affine D schemes. Okay, so for us, we want to follow sort of a algebro-geometric style and view PDEs as ideal sheaves or ideal sheaf sequences. So this A of X will always be just sheaves on the structure sheaf of jets for some bundle over X. And I will just be some differentially consistent, so system of PDEs. And then B is just the quotient. So you can really think of this I as being obtained from the formally taking all formal differential consequences of your original system. Okay, and there's a nice dictionary presented here that can show the comparison or the analogy with algebraic geometry, which we want to further between derived algebraic geometry and derived D geometry on the other side. So as I mentioned, though, you might not have this sheaf of differential operators. And another equivalent way to look at it is to look at sheaves over this de Rham space. So I don't want to say anything really about what this is, except for when you see the de Rham space, you can think of parallel transport. So it's the other way of looking at a flat connection, not necessarily a Lie algebra map between vector fields on your base, acting compatibly with fiber-wise vector fields on the total space of your bundle, but in terms of the induced parallel transport isomorphism between the fibers. This is the algebro-geometric notion of identifying fibers if the points on your manifold or your variety or scheme are infinitesimally close together. What's nice is that this applies to a lot of other settings, like X might be singular. And it's well known that sheaves of a certain type, I'll write here quasi-coherent sheaves, are equivalent as so ordinary categories, but also for in higher categorical settings with left D modules. And so one of the things we like to exploit is a sort of nonlinear avatar of this, which is commutative monoid objects in the D modules and commutative monoid objects in quasi-coherent sheaves on the de Rham space. So this is left. There's also a right version, but it's not important for us really today that what this is called. So also another terminology for these on the side is crystals of sheaves on X. It means sheaves over the de Rham space. So you can ask for crystals of other objects so that there's higher homotopically coherent identifications over close points. So if we don't just want vector bundles, we could look at, or sheaves, we could look at pre-stacks. So these are these generalized spaces or derived pre-stacks. And so you can ask for crystals of pre-stacks, and these are really the models of the objects we want. They're functors into spaces, and they take values on some DG version of these commutative affine D schemes we saw before. So D here is always going to be derived or indicate, so some kind of DG structure happening. And so again, there's a lot of infinity categorical stuff going on here, but it's not very important. All we want to know is that these we can fit our objects that we know into these spaces in a nice way, and we can learn new things. So what's one of the new things we can learn? So of course, as I mentioned, the functor of calculus in the non-singular PDE setting, the Vinogradov place, is over this filtered algebra. So Fi here is just lazy notation for the ith filtered piece of this jet tower or the associated tower on the prolongations. And so you can ask, okay, we can do some kind of, let's apply these functors of calculus to some kind of homotopical category. A typical example is model category structure. So it's self-organized into some a nice environment for doing homotopy theory. A good example is if you look at take a commutative algebra, you look at complex, DG modules over this. This is a model category, and what's important is there's a singled out class of morphisms called weak equivalences. And in these most cases we'll talk about, this is just going to be the classes of quasi-isomorphisms between your objects. Okay, so then it means if we want to do some kind of calculus in this, we better have it developed in a way that it preserves the weak equivalences. And so usually this is what people would do if in the ordinary homological algebra, you derive your functor, and then you prove that you have to pick a resolution by projective or injective objects, then you prove it's independent of such a resolution. But in this setting, it's a similar phenomena, but if you can cook things up to be infinity categories, so it preserves the class of weak equivalences, then you're in business and have some kind of higher version of your functor. And so I only want to talk about one specific functor in a specific case. If we just take commutative differential graded algebras, not in any PDE setting, just over a field of characteristic 0. So these are connective means just in non-positive degrees. The differential is homological. So it goes like a to the -1, a0, and stops there, but it goes from the negatives to the more positives. So you can do the usual game of forming Kähler differentials. From the universal properties, it'll tell you that this internal differential that comes with your DGA induces one as well in your sheaf of Kähler differentials. And this will also have an induced homological degree. And if it increases in the underlying DGA, it does so in the Kähler forms. And so you can look at what is the de Rham algebra or the de Rham complex. So a typical way to do this is to shift your complex of one forms. So keep in mind, these are all complexes now. Everything has a DG structure. And actually omega 1 of A with this D internal induced is a DG module over the CDGA A. And so If you shift by one and apply symmetric algebra functor with some homotopical subtleties under the table, it really opens up to what we would maybe understand as this usual wedge powers, but this is placed in degree, shifted by minus p. So what is this notation here? It means degree of the R object. So it'll be homological or cohomological degree k. Keep in mind that k is negative for us. And you shift it by p, and then it's in weight p. So it's just a p form. So in this language, people would say you have a cohomological degree k differential p form. Okay, and you can do the usual de Rham differential, extending it by the graded Leibniz rule in a compatible way that it anti-commutes with the internal differential. And they have the following weights and degrees. So the internal differential inherits just the same cohomological degree 1, but it doesn't change the weight. That's, I think, straightforward. And then the other one, of course, should change the weight by 1. After all, it's increasing the de Rham form, the de Rham weight, and then it has a cohomological degree of -1. We add another form in, but we don't want to change the degree. Okay, so this is one of the main things, but what really is interesting in this context is what you ask happens to symplectic forms. So keep in mind, everything is a complex now. And this is where you enter the realm of so-called shifted symplectic derived geometry. So the shift really refers to the fact that if you think about your original tangent, what you would think of as a symplectic form, it's an anti-symmetric bilinear form on the tangent complex valued in your structure sheet. Or if you want to think about it in associated like musical isomorphisms, if they would exist in this situation, it's some kind of map between the DG version of your Kähler forms. So here I've switched it to this standard notation of boldface L. This is the cotangent complex. But if you have your nice, it's basically a derived functor of the Kähler form. So if A is sufficiently nice, then I'll use these interchangeably. Otherwise, you should take a cofibrant replacement or replace your object basically by some kind of more general causal Tate type resolution, and then you can apply the Kähler structure, the Kähler functor of Kähler differentials. Okay, so in this setting, if you want to look at this musical isomorphism, it won't be asking for non-degeneracy of your form. Will definitely not be just an isomorphism of spaces. This is complexes. So this should be at the very you should be asking a weakened version, which is a quasi-isomorphism. So it's a morphism in the derived category between your cotangent complex and its dual object, which will be the tangent complex. And there should be a shift, and the shift will be depending on the degree of your form. Again, these forms are objects in a complex. They're not just elements of a vector space, so they'll have their own cohomological degree. They're maps between complexes. So in this area of derived geometry is very fascinating. You can build a simplicial set of such forms. And the cohomology spaces, or the homotopy groups of these are classes in these complexes. Okay, so this is probably a bit obscure, but what's really interesting is if you you can form the total de Rham complex of this object, which is this guy here. And it has the total differential, so you add the internal one plus the de Rham differential. And there's a filtration where you look at only those complexes of a degree at least p. And then in principle, what people do is you shift everything down by p so that the piece starting at I equals p is in degree 0. And in this complex, which is, I guess, like an analog of this Hodge filtration, which comes up in this, you can ask for cocycles of a specific degree in this filtered piece of the total de Rham complex. And what is really interesting about this is it means you can ask for what is this data of a cocycle of a given cohomological degree n in this thing. It's an infinite sequence of forms. each one coming from one of these these spaces here. So I read it omega p plus 1, blah, 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 and it goes on its semi-infinite sequence because we've taken the product total complex. They all have a specific degree. And if you compute the co-cycle condition for the total differential, so here delta is the internal differential for us, then the condition of being closed means it's closed internally as an object of the complex of p forms in degree, shifted in by minus p into, so it's in degree 0. And this is what we would expect normally from a type of closed condition, but this is in this complex, but it's together with an entire homotopically coherent set of data, which is the additional data you need to close up your form in this complex. Okay, so this is the main, again, as we saw from when you were trying to take these derived R-sol spaces, again, the condition for something to equal is really relaxed. It's now your homotopically coherent additional data. It's not a condition. And same here. It's not asking for a condition to be a closed form. It's a homotopically coherent system of identities. Okay, so going ahead, just to get to where I really want to go, I think I'm taking quite some time, is you have part of what's really important about this area is there's many new symplectic structures that exist on singular moduli spaces have been found that would otherwise be impossible to detect them. And this is because there's no good notion of degeneracy or non-degeneracy in this strict sense. But up to homotopy, you can have a lot more interesting structures. And the hope is that this is really what we see for PDEs, as I'll see. So the AKSZ and this Pantev, Toyan, Vetseltsevak formalism. So the original AKSZ is sort of this transgression. If you have some mapping space, you can push-pull your form if your target is symplectic. And this can define a transgressed form onto your mapping space. Okay, so skipping over this, in the seminal work of PTVV, this also works for DG or derived stacks when E has a shifted symplectic structure. So again, these are moduli spaces. So you can probe it with some space. So test it on something. This would be our T from before, spec of A. It's one of those parametrizing spaces. And you can see when these objects exist, they might not always, that really you can pull back the tangent complex, and you can you compute the tangent complex of your mapping spaces. Okay, so modulo, assumptions on orientability, which is very important, but for us, we're going to skip over it of your domain X. Then, for instance, if X is the smooth projective scheme or like a Calabi-Yau variety, then you have canonical orientations. But you can induce a shifted form as well on the mapping space. Okay, so for PDEs, we don't want just arbitrary maps, and we don't just want arbitrary sections, but we want to look at those sections which additionally formally solve some DG PDE object. And so the question that we really want to address is, what is the tangent complex for these things? Is there a similar evaluation type diagram, this PTVV AKSZ formalism? And if we have some DG functor of calculus on the DG version of your PDE, under the secondary philosophy, which is that it would be sort of a structure in cohomology, keep in mind that these forms, these symplectic forms that we saw before, were all elements of cohomology classes of this complex. Does this fit this philosophy? And we see that it gives the primary calculus, structure of calculus on the solution space or the space of sections. And it turns out this actually becomes even somehow more of a canonical feature of PDE geometry, at least in my opinion, in this setting, because of the nature of the objects that we work with, which I'll try to emphasize. So this is absolutely going much slower than I anticipated. So here we're just going to skip over the functor of points approach is really that you view these objects as before. You can study spaces of your D schemes. It fits our intuition, just maybe algebrogeometrically with these ideal sheaf sequences for for what a solution is in the usual sense, infinite jet prolongation factoring through your equation manifold. If you have an ideal sheaf sequence I, A to B, it means it just factors dually through it. And so again, we're looking for the necessary differential enhancement, or DG1. So just to quickly go over what this would look like in the DG metric setting. So we pass to A module, AD module. So it's A module objects in the category of D modules. So this A tensor dx, if you write this locally, this is really the identifies with the what would be the C differential operators. It's those lifted from the base, so by this distribution in total derivatives, and it has coefficients in the the algebra of jets. So we want to look up some dual-module type dualities. And so this is the so-called Verdier duality, so twisting by the dual again. And in these pictures here, I'm just showing that this really actually does give a isomorphism between coefficients in jets and differential operators between bundles and the pullbacks of the respective ones with C differential operators. So this fits our intuition, and you can actually compute what is the tangent functor, the tangent sheaf of a D algebra. If it's an infinite jet algebra of a vibration, it really is this vertical vector fields, basically. And so you have the same sort of generating map, so you have between vertical vector fields and evolutionary derivations. So again, this is computing the just derivations as a normal functor of calculus, but D-linearly. Okay, so this fits our intuition. You can look at what is the derivative of such a map between D schemes. It really is some kind of, it agrees on the nose with the formulas for linearization operator. And then Kähler differentials taken by the Verdier dual is really what we understand as these Cartan forms. And you can write them in a basis. It really are the Cartan forms in the fiber variables and the base coordinates. So now we can take the same thing. You take the symmetric algebra of the shifted forms in the category of D modules, and we can study the D module Durham complex of this guy. In particular, it is a D module, but it's a D module with a compatible action by A. Okay, so this is just to show that it really fits into the D module language, as you can sort of derive tensor products, so it's a resolution of the appropriate sheaves and it is exactly what fits our intuition. Again, we have one column of this thing is through the horizontal homology. It's the pullback of the Durham complex from the base with coefficients in A. Okay, and you can also do the same thing and now just put the p-forms, D-linear p-forms in there. And this would be basically the Cartan p-forms. And so this variational complex here will be the Durham complex pulled back from X. So with coefficients in A, tensored with this thing. This is really just the p part of the variational Bi-complex. Okay, so this is just a very abstract way of showing this idea of secondary calculus, that you pick a cohomology and it really transgresses to this space. But this is in the non-DG setting. So I really want to, in the remaining time, get to the interesting DG enhancement, what happens. So this is just the geometry, the dictionary that hopefully you could take a look at. If I distribute the slides after, you can see, then compare with your intuition if some of these objects are to match with your understanding. So the affine case for higher PDE geometry, again, so we're looking at CDGA objects, commutative differential graded D algebras. So it has a homological differential. So you can think of what we just did for the usual CDGA over K. The cohomologies of these spaces, it's just a graded D algebra. And in particular, each one of them is a D module as well. So this is because the compatibility of the differential with the action by differential operators. So it commutes, so it actually induces a D module structure on the cohomologies. Okay, so in this data, you can get the classical object, which is the so-called classical truncation. You just take the H0 of your CDGA because it's truncated at at 0, they're non-positive. This is a commutative D algebra in the usual sense, and you can take the D spectrum of this. So this is really reminiscent to the causal Tate example from before. It fits into this, the classical truncation recovers your classical locus. Okay, and so you can form, it has a lot of extra data just floating around in it, which is quite nice at the level of cohomologies anyways. And we want to view all these objects glued up to weak equivalent, so quasi-isomorphism. You can formulate the so-called derived functors of their mapping spaces, Verdier dualities, and formulate some various interesting D-module dualities for these AD modules. So this is really to be thought of as this a derived category of C complexes, I guess, in the language of Vinogradov secondary calculus. This homotopy category of DGA is really the derived category of bounded complexes of perfect D modules over A. Okay, so in this setting, we can find a derived functor of the Kähler construction we saw before. Again, this is underlying A is differential graded. So this will be, again, a complex of one forms. And you can take a co-fibered resolution. It's a canonical operation in this model category of objects. And it produces for you the correct, homotopically correct Kähler construction. And so our so-called tangent complex will just be then the appropriate D module or Verdier dual object of this. This is because L of A, the D geometric cotangent complex, is a D module, which means a module, a differential graded A module in left D modules. Dualizing it, as I said before, it produces for us a right AD module. So tensoring again, twisting by this dualizing sheaf will produce us back an object. So this is a functorial construction. Okay, and so if you play the exact same game with, as we saw before with the shifted symplectic structures, you can cook up what is this symmetric, maybe I put it here, the de Rham algebra of this. So this is shown for a specific, very specific case of a free D algebra. This is the free symmetric algebra on a compact D module. So in a homotopy sense, compact D module is perfect complex of D modules. Okay, so in this specific case, this de Rham algebra construction agrees with what we did for the usual differential graded setting for derived K algebras, not D algebras. So we shift by one, and we take the symmetric algebra. So there's an interesting fact that the D module structure splits your complex. It's a sort of Ehresmann connection, which is induced from the fact that it's a flat connection. And so what does this thing look like? This for us is essentially the vertical vector fields plus ones on the base. I'm omitting a pullback operation here for convenience of notation, but this L of X, if X is smooth, this is just the usual tangent space of the base. So I'm reserving the notation boldface of L here because this really does hold for singular schemes. Or singular varieties in the base manifold. And also for spaces potentially with like manifolds with corners, or for example, if you wanted to consider manifold bordered spaces. This is important for PDE applications for growth conditions for manifolds with, let's say, cylindrical ends and stuff. So anyway, so it splits. The symmetric algebra splits. And so what is this? This is just the horizontal piece. This is the horizontal characteristic complex, if this is, a ordinary tangent space. And this one would be the DG version of the Cartan forms now, the vertical forms here. So you can play more or less the same game modulo some D module nuances and cook up a simplicial set of forms in this total de Rham complex. We want to take the product totalization of this total complex. And you can look at, again, it's a sort of Hodge filtration. So you only look at those it's going to be bi-filtered, obviously, because of the splitting that we just saw. It's a bi-complex after all, but now it's sort of a DG in one direction. And so this Hodge filtration filters your complex again. So you look at only the filtration, so the pieces in degree, let's say, T and higher, but T splits by the bi-complex decomposition. So into R plus S. S will be the Cartan. There should be a wedge product here, sorry. So S Cartan forms, but now they have a DG structure. So it's a complex here. And this is just a vector. This is just the usual differential forms I've written here for a complex manifold. Okay, so now you can write out an element here. So we've shifted back appropriately. So they have homological degree inherited from this thing. So some huge semi-infinite sequence. But now we have, I guess, twice as many equations because we have we have an additional two relations coming from our complex that you'll see soon. This comes from the splitting. So this is just mumbo jumbo up here to say, okay, this actually is homotopically well defined. Everything preserves, as I said, quasi-isomorphisms. So it's a functor, it enhances itself to actually an infinity functor. Here it's formulated model categorically, which means if you take the derived functor, it induces a functor on the homotopy categories. And this is the case if it preserves weak equivalences, which is better otherwise. We're in no business be doing homotopy theory with these objects. So freezing this so-called tri-complex at a given term, it's looks like this. So we have the PQ forms of degree K. So note that this is there should be little wedge products here for all of these ones. And so these are, again, this is usually, as we're familiar with, this is a vector space, or this is just an ordinary vector space of forms. But in general, we have complexes now in each term. So they put into, again, shifted into degree by the degree of your Kähler forms, the DG Kähler forms here. So here it's written with Q. This is the cofibrant replacement. So it'd be resolving your DG algebra B by some nice resolution type object, so by these semi-free objects basically, and so I have a correct homotopically defined Kähler cotangent complex. And so this is the way the differentials interact with the various degrees and shifts. So as you see, the vertical one and the internal one that's inherited here is very much the same as in the shifted symplectic setting, as we saw before. The additional one is that we have the horizontal guy floating around, and this is purely a horizontal contribution pulled back. And so now it makes sense to ask, in this total complex, where the differential is a sum of the three, what is a cocycle of a given homological degree? So this is n cocycle in this big complex of objects. And again, so you would, if you write it out, you have some, using this description of the forms here. This one is annihilated by the internal differential delta, as in the other case. But now we have a contribution coming from inside the page, out of the page, as I think I've written it. Yeah, so the homological, it's a cochain complex, stops at 0, goes minus, minus, minus into the page. So it's coming out of the page. So you have additional contributions that come in from out of the page. And one is of a different horizontal form, and one's coming from a different vertical or cartan degree. And you just play the same game as asking, okay, how do we close this up with the homotopical coherent data? So here's just some additional structures. You've got the usual wedge that respects all of the various gradings in the natural way that you would expect. So this is, I guess, what it looks like. You have, if we're assuming completely non-positive CDGAs in the category of D modules, then it stops at 0. The homological one takes us out of the page. And then we have the horizontal and vertical one, and we take the total complex with respect to this. So again, the vertical, if we're assuming that our base space X is smooth, then we just have it's concentrated in the usual degrees, 0 to the dimension of the base. But the vertical one is now sort of infinite in the two directions. It's infinite in the usual jet direction, and it's also infinite in the a priori infinite in the cotangent complex direction induced. But there's there might also be situations where it has positive concentration, but we don't talk about this. It's not important for us. So again, here's just a few of the relations that you might see if you write out the cocycle condition. So you have the homological degree n form as an n cocycle, but it's shifted into degree 0. It's a p horizontal legs, q vertical legs. The q vertical legs each contribute a factor of some degree, and the degrees add up to be the n. And so it's killed by the internal differential, the homological one. And then you have the compatibility conditions coming from each of the remaining homotopy coherent data. So you have the ones from the n-1, from the q plus 1, and the p plus 1. And these interact with the horizontal, and then it continues this way. And it's, again, in general, an infinite system of relations you need to make the form closed. So this is, I suppose I should finish up. But one thing I would like to mention at this point before I go, just say the final things about what this looks like when you look at this cotangent complex, and can we transgress and find some kind of induced structure on the space of solutions, is that it's still a priori unclear if these appear in PDE geometry. Are there closures? Are there maybe new conservation laws or higher conserved quantities that hold up to homotopy only? This is something I think is really an interesting question that I want to pursue in detail, as I think with the notion of shifted symplectic structures, we found a lot of new forms that existed on moduli spaces that were unseen. You couldn't even detect them before you used some homotopy machinery. So it could be interesting to see if these appear. One example where such a similar setup has been applied, and where which actually fits into this larger framework of derived tricomplexes, is I think it's also called variational tricomplex in the classical PDE jet space literature, where instead of resolving your equation manifold or you're enhancing your equation, you look at the bundle itself, and you want to maybe make this bundle give it an odd a z grading and a homological vector field, let's say Q. Then Q is basically this role of delta. And why would you want to do this? Well, in principle, this is a nice practical model for the BV formalism, where this additional z grading is the ghost degree. And I have to admit, I forget who the author, perhaps it was Henno, I'm not sure, or Teitelbaum, but they have some interesting papers where they compute the cohomologies in this with respect to this additional tricomplex grading corresponding to ghost degree in the bicomplex. And it has relations to various Lie algebras of symmetries. And so it would be very interesting in this setting to see what kind of higher symmetries we have for our DG Lie algebra. Okay, and just to finish, you can play the same game for these over the de Rham space. And this is almost verbatim a nice little application in infinity category and functorial stuff of the classical results of Marvin about this jet coalgebra. It's now an infinity comonad. And you can study jet spaces in this setting. You can form mapping spaces. And in particular, you can ask, if you have such a Z that is formed by this DG jet construction now, and you look at some homotopically closed subspace, what is the mapping space of this? Well, it's defined actually by a universal property called derived Weil restriction. And so it satisfies a junction here of mapping spaces. And by definition, it comes with a universal family like this. So there's an evaluation, what we sought for before, and there's a projection. And so if we have such a cotangent complex in the D setting, the Z would have been our A before, or structured D scheme with structure sheaf A. Then we can play the same game. We pull it back, and can we push it down, and can we induce symplectic structures on the solution space here? Well, this question is more subtle, I think, than in the usual setting because of the functorialities. Everything is over x to rom relative. So functorialities relative to x to rom are, in fact, de Rham cohomologies by general functor, like the six-functor formalism. So it means if you take a T point, it corresponds to a T parameterized infinite jet of a section. And you could pull back the cotangent complex if it exists. And you get an OZ DG module. Remember, this was A in sheaves on x to rom. But these were, as I said before, morally D modules. So we have an A DG module in D modules. So an AD module, as we saw before. It's all just very derived now and homotopical. And then the push forward from the de Rham space to a point is just global sections over x to rom, and this is just de Rham cohomology. And so to conclude, I want to just emphasize that the secondary philosophy, in fact, is it fits in perfectly because when you have such a cotangent complex of Z relative to x to rom, by the functorialities relative to x to rom of our sheaves, when you pull it back, you have this nice relation between as sort of in the mapping space one. But these four functorialities are very special. And in particular, at a given solution, at a T point, you end up with this relation between the tangent complex of your stack, of your R sol, and this DG sheaf of relative to the base of the D geometric tangent complex. And this is exactly de Rham cohomology. So what is this saying? It means that you have, if there is some tangent secondary, this is basically the secondary object. It's the cohomology class of a DG version of the tangent space to your DG PDE. If you were just in the classical setting, this is honestly the tangent sheaf to the PDE. This is just the Kähler, the usual the universal, the sheaf of evolutionary derivations here. And in fact, this really is a sort of manifestation of secondary calculus in a purely derived language. And then, so I should end now and just say that there is the complex, variational complex pops up here too. And upon fixing a orientation, which over smooth bases is just a choice of fundamental class. So some kind of Poincaré duality here, that we can indeed pass to the simplicial sets, pull back, and you can transgress certain forms of a fixed horizontal degree from the variational bi-complex to the space of solutions in a homotopically coherent way. So Q here is this, again, this vertical form. So so yes, that's, I should end now. And so what we do, there's some DG enhancement to these objects. It should connect nicely to known things, and maybe we can try to probe and find some new conservation laws, calculate some new invariants. But this remains to be seen, and I'm very interested in pursuing this and talking to more people in the PDE community about these topics. So I should say stop now and say thank you very much for your attention. I apologize for my overrunning the time.
Okay, Jakub, thanks a lot. Questions, remarks? No question, no remark. Then I have one request and two questions. First, you, well, I think quite briefly mentioned how to construct tangent objects, yes? And do you have any ideas about cotangent space too?
The cotangent space, yes. So the cotangent space is morally it's the D-module dual of our tangent space. So it has this derived duality between the two in the derived category of objects. So formally, it was specified as a duality here. So this D of A is R hom like this. So what is this? This can really be seen as in the classical setting as something very familiar when this is just the Cartan forms, and this is identified with the algebra of symmetries. And there's a twist here of the again, this R hom, AD linear R hom is really, you can view it as C differential operators. So this is sort of this fundamental isomorphism on jet spaces of the sheaf or the module. I forget exactly what the terminology for it. It's that var kappa and is equal to C differential operator of the Cartan forms with values in the module, the horizontal forms. So this gives you reproduces in the DG setting this sort of fundamental isomorphism. It's important that it has to be the D module, the AD linear dual, not the A linear dual. Otherwise, the dualities are broken. So you need to use this D module duality as well, which maybe it explains sort of this adjoint. It's sort of this sort of formally like a formal adjoint type operation at the level of differential operators.
And the second question, this tri-complex, which you constructed in the end, did you try to compute it for some specific PDEs?
So for specific PDEs, I have written out all of the relations for just a PDE that is so on, let's say, a two-dimensional manifold, but not a specific PDE as an example, but when the tangent complex is just two terms. So you have just your usual one, and in here, it's just the usual cotangent complex A is just the Kähler differentials there. And then the next term is just sort of the conormal sheaf of your ideal that defines your equation. And so in this case, it's a particularly, it simplifies, but I haven't computed any homology classes in this yet for specific PDEs.
Yes, I meant homology classes, of course.
Yeah.
What do you think for this tri-complex? Do there exist results similar to Vinogradov's P-line theorem?
Yeah, so this is interesting. I think so. This cofibrant replacement here was shown in this model category of D algebras. It's shown to provide a more general setting of both the causal Tate resolution of your on-shell algebra functions and the compatibility complex of your operator. By who wrote it? Norbert Ponstein, his student Damian Pistallo, and Gennaro Debrino, I think, wrote this in 2018. And they show that all of these PDE theoretic sort of resolution techniques are part of this cofibrant replacement. So what does that mean? It means it's a recording of the homological finitude of your PDEs. as they have finite resolution, it corresponds to sort of the length of this compatibility complex.
Yes, of course.
So it'd be interesting to see if this has a explicit, appears somewhere explicitly for, yeah, for the, so for example, one of the things that was worked out is if you take the DG algebra of, so this is just the Euler-Lagrange equations, you can, such a cofibrant replacement or is a causal Tate resolution that resolves this depends on sort of the symmetries of your, depending on your action functional. And in the case of Chern-Simons or Yang-Mills, it agrees with the, if you compute this cofibrant replacement and the tangent complex, it agrees with the compatibility complex for Yang-Mills exactly how it was written by Dmitry Geisler, I think, in one of his papers about the something 3-line theorem for Yang-Mills or something like this. So it's exactly the resolution he wrote for the linearization operator. The first term is the adjoint of the gauge symmetry. And so you really do have this algebra that resolves your algebra of functions, but again, it's not quite a resolution, it's a cofibrant replacement. And what that means is you can take homology of it. So pi1 or h1 or h minus 1 is the Noether symmetries, but they're built in. So h higher order cohomologies of that object will correspond to higher order Noether symmetries. So in general, if you compute the cohomologies of this, these symplectic forms, these huge, this huge family of them that contributes to your shifted symplectic structure in this setting are all elements of cohomology classes of appropriate type. And so it's likely that their existence will be influenced by that, especially in the case that's related to gauge symmetries, to higher order Noether symmetries.
Thanks a lot. Okay, and the request, please, if you don't object, send me or to the seminar address your slides.
Okay, yes, absolutely.
Okay? Yeah, thanks a lot.
So
Okay,
thank you.
Jakob, thanks a lot. So we meet in a week. If I am correct, there will be talk by Valentin Luchagin, and I believe it will be very interesting. So everyone is invited. Thank you for being here, and goodbye.